What's up, stats? This is Mr. Carlson, and we are going to be doing 3.4 additional topics in probability. So last week we did all of our probability lessons, 3.1, 3.2, 3.3 on the basics of probability, the AND rule, which in other words, it's the multiplication rule, and then the OR rule, which is the addition rule. How can we add things together, mutual exclusive events, independency, dependency, multiplication? We did all of that. We even did some two-way frequency tables. And so this week is going to be a very short week, in that we're going to do additional topics in probability and how we can use the fundamental counting principle to our advantage when looking at how many different ways can something occur. And we're also going to be looking more in depth with two-way frequency tables. We're going to do bell work. We're going to go through 3.4, and then, of course, the summary, the conclusion, and then the homework. Let's do it. These are the two questions I had on the probabilities quiz that I thought that it was beneficial for us to go through. So let's get through them. This first one, 2 cards are selected from a standard deck of 52 cards. The first is replaced before the second card is selected. So the first is replaced. That means automatically that this is going to be independent. The reason why it's independent events is because the first card does not affect the second card being drawn. Because it's replaced, that means my total when I select the second card is not going to change. It's still going to be 52 cards. So since each draw does not affect the other, it's what we call independent events. So the second step in my problem is to then do the actual math. Find the probability of selecting a spade. So we have the probability of selecting a spade, and means multiplied, so and then a king. Okay? So what's the probability of selecting a spade? Well, there's 13 spades in the card deck out of 52 cards times, and then how many kings? There's 4 kings in the total deck. Remember, my total doesn't change because the first card is replaced after I drew it. So it's still going to be 52 cards. Multiply this together. This is 52 all over 2,704 when I multiply across. And so this reduces down to 1 out of 52. All I need to do is just plug that into Desmos, and then it'll simplify it for me. That's all I need to do. I'll show you right now. 52, all over 2,704. So 52 divided by 2,704 gives me that. And then I can put it into a fraction instead of a decimal, and it simplifies it for me, 1 out of 52. Which is awesome. So that is how we do that first question. Very simple, very cut and dry. Second question, use a frequency distribution right here off to the right, which shows the number of voters in millions according to the age. So what we want to do is find the probability that the voter chosen at random is in the given age range. So not between 45 and 64. So the probability of it not between 45 and 64 equals our probability. But the problem is here, what we need to do first and foremost, before we even touch this probability, since it's not, I know it's going to be 1 minus something because we're doing a complement, and that's what complement means, 1 minus something. But I need to figure out how much is this total. What's the actual total here? I don't know that, so that's what I need to find. So I need to add all this stuff up. Once I add all this stuff up, I get 154.7. So the total frequency is 154.7. That's the total number of voters in millions. So 154,700,000. Okay, that's what it's saying. Now I can take that total and finally put it into my probability. Now what goes in the numerator? What goes in the numerator is the probability that we're interested in. So 45 out of 64, so I want to take that 58.8. The reason why I want to take that 58.8 is because what I'm trying to do is take that piece out. So we want to know everything else besides this. So I want to know all of this, and all of the 65 and over, but I don't want to know this little piece. So because I don't want to know that little piece, this 45 to 64, then that means I need to take it out of my 100%. When I do that, it simplifies down to 0.6199, or roughly 62%, which means 62% of my voters are not between 45 to 64. Okay, which also means about 38% of my voters are between 60 or 45 to 64. So this is roughly around 38% because that's a complement. Okay, and then everything else is 62% roughly. Okay, so those are the two questions I want to go through, bell work. I don't want to take up any more time on that, so let's erase and let's get started on the actual notes. Oh shoot, totally forgot I had this question. Well, we can definitely go through it. Let's go to town on it. Really simple. So the access code for the safe consists of 3 digits. So each digit can be any number between 0 and 6. So then we have to count. Okay, how many digits is that? 0, 1, 2, 3, 4, 5, 6. So that means we have 7, not 6, 7, because we have to include the 0 there. So each digit can be repeated. So then when it asks us find the number of possible access codes, we have 7 different possible access codes. So 7 times 7 times 7. Oops, forgot one thing. Forgot to read one thing. 3 digits. So we have 3 digits. So 7 possible numbers, yes. Okay, but 3 digits. Okay, so that's what I'm going to do right here. So I only did 3. So sorry about that. Let's go back. I only did 3 digits, 1, 2, 3, 3 spaces, and how many digits from those 3? There's 7 total. We multiply it together, 7 cubed. If we don't know what that is, we can go to Desmos, do 7 cubed real quick. Oh my gosh. 243. So then we can go over here and actually say 343 possible access codes. Okay. Now, B is going to ask what's the probability of selecting the correct one? Well, there's only one correct one, especially on the first try. So 1 all over 343. You can put it in a decimal if you want, but I'm not going to. I'm going to leave it at that. And then C, what's the probability of not selecting it? So the probability of not selecting the correct access code is equal to 1 minus 1 all over 343. So this is the probability of selecting the correct access code. What's the probability of not selecting the correct access code? It is that. So then we go back to Desmos real quick, and we can do that. So 1 minus 1 divided by 343. So it's about 0.9971. 0.9971 to round. 0.9971. About 99% of not getting the correct access code the first time. So that's what I have. Awesome. So that question, sorry, I forgot I put it on there, but we went over it, so that's fantastic. Let's erase. I hope that makes a little bit more sense now. And let's get started on the actual notes. So additional topics and probability. I really like this topic because it's very interesting. There's a lot of application questions to it. So remember, you can always print off the key on Google Classroom. You can always print off the notes as well, or the key and the notes, and just copy down yourself, follow along. Instead of maybe watching the video, you can absolutely do that. But since you're here, might as well just follow along. What we can do is find the number, hopefully at the end, we can find the number of ways a group of objects can be arranged by using permutations and combinations. So we're going to learn about what that is. That's actually going to take the vast majority of our time today. And then we can find probabilities using counting principles. That's what we're going to be doing. How do I find the number of ways a group of objects can be arranged? And how do I find probabilities using counting principles? Awesome. So our first thing, permutation is an ordered arrangement, of objects. The number of different permutations of n distinct objects is n factorial. It doesn't mean like n because it has an exclamation point. It just means n factorial. N factorial. That's what it's going to be called. Okay, and so right here, the expression n exclamation point is read n factorial. Okay, that's what it's read as. Okay. So if n is a positive integer, then n factorial is defined as follows. So n factorial means simply this, guys: n times n minus 1 times n minus 2 times n minus 3, and then literally and so on and so forth. So it's 3 times 2 times 1 all the way until you get to 1. Okay, what does that mean for us? That means if I have 1 factorial, we actually just say that's 1. But what's 2 factorial? That means 2 times 1, which equals 2. Okay? 3 factorial is 3 times 2 times 1, which equals 6. And this is 4 times 3 times 2 times 1, which equals 24. Okay, 4 times 3 is 12, times 2 is 24, times 1 is still 24. So that is how we do factorials. It's just kind of counting down. If I have 5 factorial, it's 5 times 4 times 3 times 2 times 1. If I have 10 factorial, it's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, and so forth. So it's a lot of stuff, but that's okay because we have a calculator that can do it. But I wanted to introduce that factorial, and that's how we do it. So let's actually use the factorial in an actual problem regarding permutations. Hopefully an actual problem that we're used to. The objective of a 9x9 Sudoku puzzle is to fill the grid so that each row, each column, in each 3x3 grid contains the digits 1 through 9. So how do I do that? Well, if we look at this is what a Sudoku puzzle is. Okay, so I notice this to be, let's just say that this is, let's just look at this 1 here. So there's a 1 right here and a 1 right here. That means in this row, there's a 1 in that row, 1 in that row, and 1 in this box, and then 1 in this box. So that means there needs to be a 1 in this box, and it needs to be either right here or right here. Okay, but since we don't know which box it is, we have to kind of keep it isolated right now until we come back to it. Now, if there's a 1 that was chilling like in one of these rows, then clearly we wouldn't be able to do that. But let's look at a different number just to kind of get a sense of what this is. Let's look at 7 and then 7. So I know there's a 7 in this row, okay? So 7 in this row. So that means there can't be any 7 in this box. There can't be any 7 in right there at all because there's a 7 already here. There can't be a 7 or a 7 in that box. So we're really trying to find if there's a 7 here or if there's a 7 here. Okay, because there's already a 7 in that box, there's already a 7 in that box. All right, so we look, okay, what about those? Well, there's a 7 in this row right here. So that means there has to be a 7 right there. Okay, that's just the basics of how Sudoku works. You can do a lot more other puzzles like that as well, other strategies in order to solve this puzzle. We're not going to spend any more time on that because, again, that's not what we're trying to learn. Okay, what we're trying to learn is how many different ways can the first row of a blank 9x9 Sudoku grid can be filled. Well, we just use our permutations, of course, and our factorials. So that means 9 factorial equals, okay, because there's 9 different options. And so that is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 equals some number. Now, what is that number? Well, if we go to our calculator, Desmos, we can go to our calculator and we can actually literally type in 9 and then exclamation point, and it actually gives us the answer, which is pretty fantastic. Okay, and so that's why and that's how we can do that. Okay, so now we can go over here and we can actually type that number in. So it's 362,880 different ways. Okay, so that's how you do permutations, factorials. Let's go through a different example. So the teams of a league central division are listed below. How many different ways can the final standings how many different final standings are possible? Well, there's six. There's six of them, right? So 1, 2, 3, 4, 5. There's six. So that's just 6 factorial. So that's 6 times 5 times 4 times 3 times 2 times 1. Okay? And then we can go again back to Desmos if we would like and just change that number to a 6. And then boom, we got 720, which means we go back here and we just type in 720. We write that in. So 700 in different possible standings. 720 different possible standings. Perfect. So this is how you would do permutations or basically factorials, okay? Now there's a different kind of permutations that we're going to learn next, and that is going to be permutations of different objects taken at a time, okay? I'm going to show you what that means. So permutations of n objects taken at a time, at a time. What does that mean? Well, it's this formula right here. It's actually not that scary because, again, we can use Desmos and it helps us out a lot. But what this means is NPR. So NPR. I want to say NPR because of our school. But NPR. So n factorial divided by n minus r factorial. Okay, that's what it means. Don't pay attention to the comma. Okay, where n is greater than r is greater than n. So r is greater than n. What does that mean? That means r has to be less than n always. Always, always, always. So you can take something out of something. So if I have a class of 30 kids and I say, hey, 10 of you come with me to the principal's office. Now, depending upon the order, okay, like I could have Sally, Jim, Bob, Jones, whatever, and doesn't matter the order. However, when it comes to permutations, it does matter the order, okay? So that's the first thing I want to say. The order does matter. Order does matter. Okay? That's what it means. Order does matter. It has to matter. So if I do take those 10 students from my classroom to go to the principal's office, that means that I need to arrange them in such a way. And then how many different ways can I actually arrange them? That's what I'm thinking about. But I'm taking 30 permutation 10. So 30 kids total in my class, but I'm taking 10 out of my class. Okay, and another way we can think about it is find the number of ways forming 4-digit codes in which no digit can be repeated. What does that look like? Well, how many digits do we have? Well, including 0, we have 10. Okay, and there's 4 digits that we're taking out of that 10. So that means NPR equals 10P4. Why? Because I can't take 10 out of 4, but I can take 4 out of 10. And so I have 4-digit codes, but I have 10 total digits in which no digit can be repeated. So that means because no digit can be repeated, that means the order does matter. So order matters. That's how I know the order matters, and that's how I know it's a permutation, because I can't repeat the digits. So 4-digit codes in which no digit is repeated, I can do it as a permutation like this. Okay, so what is this? Well, this equals, following my formula, 10, because that's my n, factorial, 10 factorial, following my formula, divided by, parentheses, 10, because that's my n, minus my r, which is 4, and then factorial. Okay, this equals 10 factorial all over. 10 minus 4 is 6 factorial. Okay, and so what this equals then is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 factorial. Okay? Sorry, I'm not going to actually put the factorial there. This is the evaluation of the factorial. But that's what 10 factorial means, 10 times 8 times 7 times 6, and so on. Okay? All over 6 times 5 times 4 times 3 times 2 times 1. So now what you start to see is this, guys, is that these ones, the twos, the threes, the fours, the fives, and the sixes go poofy. So what am I really left with? I'm really left with that. So this equals 10 times 9 times 8 times 7 equals some number. After we plug into the calculator, I get 5,040. Now, this may be something similar to what we've already done. You may notice it, 4-digit codes in which no digit can be repeated. Okay, well, we've already done this, though, haven't we? I mean, we've already done what we've done in the past. We've actually just put okay, we have 4-digit codes, and there's 10 digits, but since I can't repeat it, I have to go down each one, right? So, however we got it there, this is what we call the fundamental counting principle, by the way. So this is what we call the fundamental counting principle. But the fundamental counting principle is what it is because of the permutations. Okay, so now we're going kind of backwards, and we're trying to find out how we have the fundamental counting principle, and it is because of permutations. Okay. This next one, the psychologist shows a list of 8 activities to her subject. How many different ways can she pick a first, second, and third activity in that order? So then what we would do is we would say, okay, well, n has to be the bigger number. So 8, r equals the smaller number, which is 3. So 8p3 equals, and then so this is 8 factorial all over, and then we have 8 minus 3 factorial. Okay, this equals 8 factorial. 8 minus 3 is 5 factorial, which then is 8 times 7 times 6 times 5. Watch what I do here, factorial. I'm not going to finish the whole string here because on the bottom I already have 5 factorial. So then these actually go poofy, and then I'm just left with 8 times 7 times 6, which reduces down to 336. That's what my final answer is. That's how many different ways that the psychologist can list her 8 activities while taking 3 at a time, first, second, and third activity. Okay, so that's the only times I'm going to actually do this by hand. The rest of the time I'm going to use Desmos. I'm actually going to show you just how to do it on the calculator. Because sometimes these can get pretty big, okay? But this is how you would do it by hand. Let's go through a couple more problems. Okay, so a 43 car race, 43 car race started the Daytona 500, the 2013 Daytona 500. How many different ways can the cars finish first, second, and third? So my R is 3, but what's my N? My N is the total, 43. So 43, and then my R is 3. So what is this? I have 43 P3. How do I do this? Well, this is 43 permutation all the way over 43, not 40, 43 minus 3, and then permutation. Okay, this is rather lengthy, okay? Very lengthy indeed. Now, you could still do it, technically, yes, but it is very, very lengthy. How do I do it, though, using technology? We're going to be using Desmos because it's the online free calculator. How do I do that? Well, I'm going to show you what you will do on Desmos, really, and it's this. You'll see this NPR, and then you'll see parentheses, and you'll literally type it in like this on Desmos, okay? This is how you'll type it in on Desmos, so make sure you get that down, and then we'll get the answer right here, okay? So let's go to Desmos real quick. We'll type it in, N, capital P, R, and then I need parentheses, 43, comma, and then I need to type my R in, which is 3, okay? Now, also on Desmos, they have the actual function available to you. So down here, the show keypad, you go over to functions, you go over to stats, and then you start to see this NPR right here. Okay, that's what it is. Okay, perfect. That's what it is. So what's my actual answer? 74,046. I'll go over here. So my answer is 74,046 different ways that those cars can finish first, second, or third. That's a lot of different ways if you really think about it. You don't really think that it's that many ways, but it truly is that many ways. Okay. Board of directors has a company, has 12 members. One member is president, vice president, secretary, and treasurer. So that means my N, what's my total? 12. And then my R, taken at a time, are those four positions. So 4. So now I have 12P4. And then if we plug that into Desmos, we'll get an answer. So I'll actually just scroll over here, erase that, 12. And then I'll go over here and then P4. What's my answer? 11,880. And it's that simple, guys. Really, seriously, it's just that simple. So 11,880 different ways that these positions can be actually assigned. That simple. A lot of now what we're going to be doing, guys, moving forward is really going to be just straight Desmos. So if we're not familiar with Desmos, if we're not getting used to Desmos at all, then that's an issue, because literally all next week is pretty much Desmos.com. The vast majority of it. And then after that is going to be our stats unit, and stats is strongly being utilized using Desmos. So it's going to be taught using Desmos. So make sure we know and are familiar with it. Now, before moving on to combinations, which is the second part of the lesson, I'm going to be going through what we call distinguishable permutations. So distinguishable permutations are this of n objects where n1 it's n sub 1 are of one type, n sub 2 are of another type, and so on. And this is your formula. Okay, that's our formula. Well, what does this mean, though? And that's really what we need to get at. Okay, so what if I have something like this? So using the formula for distinguishable permutations, you can determine that the number of distinguishable permutations of the letters A, B, B, C, C is what? So I'm going to show you right up here. Okay, how do I do that? Okay, well, if I have A, that's 4, I have 2 B's, and I have 1 C. But total together, I have 7. So the total objects is 7 factorial all over, following my formula, the different types or the different letters. So I have 4 A's times the 2 B's, so 2 factorial, and then times my 1 C. Okay, and then when I do this, I have just 7 times 6 times 5. Okay, and then all over 2. So when I actually multiply all this out, it starts simplifying and everything, and then eventually I get 105. Now I'm not going to show you the simplification, but I'm just basically showing you how I would start the problem. That's all, how I would roughly start the problem, okay? So now let's actually go through a problem so we can see how it is simplified. So a building contractor is planning to develop a subdivision. The subdivision is to consist of 6 one-story houses, 4 two-story houses, and 2 split-level houses. And how many distinguishable, that's the key word, that means we're going to use our distinguishable permutations formula. How many distinguishable ways can the houses be arranged? Well, I first need to find the total. So what's the total different options? So my N equals 6 one-story houses, and then 4 two-story houses, and then 2 split-level. So this is a total of 12 different houses. That's not my answer, okay, but that's the total. So that means I now can do my permutation formula. 12 factorial all over 6 factorial times 4 factorial times 2 factorial. Okay, and then I can literally just plug this into my calculator. Okay, so I'm going to go to Desmos, and I'm going to type that in. So 12 factorial divided by 6 factorial, and 4 factorial, and 2 factorial. And you don't need to put multiplication signs in between because they already will register as multiplication. Okay, so boom, that's my answer, 13,860. I'll go back over here, and so we can do that, 13,860 different ways. that are distinguishable is what we say, that are distinguishable. So my next one, contractor wants now to plant 6 oak trees, 9 maple trees, 5 poplar trees along the subdivision. So first off, I need to find my n. So 6 plus 9 plus 5, which equals 20. So that means my second step is to do 20 factorial all over 6 factorial times 9 factorial times 5 factorial. So then go back to Desmos, and then we can actually simplify this out. So I don't want 12 now, I want 20. And then I can go down. Why can't I go down? That is annoying. Stupid. 5 factorial, and then right here I have 9 factorial. So this is a rather large number, 77,597,520. Okay, so 77 million. Okay, let's finish this out. I have 77,597,520 different ways. So really big ways, a lot. Yes, it is pretty huge, but it's the right answer, which is really awesome. So smiley face, we're solid. Okay, let's move on to combinations. So combinations are the second thing that we're going to go over. After that, we're going to be going through some probabilities, putting everything together with the fundamental counting principle, permutations, combinations, and so forth. Very similar to permutations, but combination is a selection of R objects from a group of N objects without regard to order. So without regard to order. That's the important part, without regard to order. Okay, and is denoted by NCR. So not NPR, but NCR. The number of combinations of an object selected from a group of N objects is this formula. So it's NCR equals N factorial all over N minus R factorial times R factorial. So this is really nice because it's pretty much the exact same formula. The only difference is it tags on the R factorial there. That's really the only difference. Okay, so order does not matter. So think about this. ABC is the same thing as BAC. So in that sense, order doesn't matter. I don't care about rank. Like your class rank, order does matter, right? If I want first, second, or third place, order does matter. But if I'm just organizing just random cats or random unicorns together, it doesn't matter if I have George, Biff, or Sally. I can do Biff, Sally, and then George. It doesn't matter. Okay? So let's erase. Let's go through this example. State's Department of Transportation plans to develop a new section of interstate highway and receives 16 bids for the project. Okay, so automatically I'm going to have N equals 16. The state plans to hire 4 of the building companies. Okay, so that means out of 16, I want to hire 4. How many different combinations can be selected from 16 bidding companies? Well, I'll have 16C4, which is the same thing as 16 factorial all over 16 minus 4 factorial times 4 factorial. So if we solve this by hand, just like what we did with permutations, what it will look like is 16 factorial all over 12 factorial and then times 4 factorial, which equals 16 times 15 times 14 times 13 times 12 factorial, and then all over 12 factorial times 4 factorial. Now, of course, the 12s go proofy, and then we could continue it out if we wanted to, but it is kind of complicated. You see that this is kind of complicated because usually they would go proofy for permutations, but here you have something added. Okay, you have this added. So we have to still divide by that. And so that's why it's probably easier to just simply go and do this. So I'm going to go straight from the beginning of the problem, so NCR, because I don't want to solve it out by hand. I just want to see what it looks like on the calculator, solving it out that way. So NCR, and I had 16 as my N, comma 4. So I have 1,820. So if I go back, I know that this reduces down to 1,820 if I were to continue it, or I could have just plugged that into Desmos and I would still get the same answer, which from now on I will do, okay? So let's go on to the next one. The manager of an accounting department wants to form a 3-person committee. So that could be my N, that could be my R, but let's continue reading. Committee or advisory. From 20 employees in the department. So 20 employees from the department, what does that mean? That means that's my N. It always has to be greater. I can't take 20 out of 3, but I can take 3 out of 20. So that means I have 20 C3. So that means I can go back here and I can change this stuff. So 20 and then C3. And so now what I have is 1,140. I can go back and do 1,140 different ways. I can arrange that where order doesn't matter. So the important part is for combinations, and I'll erase this so we can summarize this. Oh, well, I have another application question. That's okay, but I just want to summarize it real quick, and you'll see this on the actual notes. I just put it right here. The summary is this, that for permutations, order does matter. So I'm going to abbreviate there. For permutations, order does matter. For combinations, though, okay, order does not matter. So if I want a combination, order does not matter. All right? Permutations, order matters. Combinations, order does not matter. So let's go through a couple application questions just by finding some probability, and this will be our our third and final couple examples here. So putting it all together, what do we have? A student advisory board consists of 17 members. 3 members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve any of the positions. Okay, that's all right. But what is the probability? Now we're introducing probability now that we have some probability underneath our skin, and now we're going to put everything together. What is the probability of selecting at random the 3? So the 3 members who currently hold the 3 positions. Okay, so this is very tricky, but let's try to do it step by step. So the first things first, is a permutation or combination? And the reason why I'm doing permutation here is because it is a rank. So a secretary, chair, and webmaster. It does matter who gets in there. Now, each member is equally likely to serve any of the positions. That's what the problem says, yes. But that doesn't mean that doesn't matter who actually serves the positions. Okay? It does matter ultimately who serves the positions, so that's why I'm going to use permutations. Now this is 17 members total with 3 positions. And if we plug this into Desmos, I'm not going to show you that step, but if we do plug that into Desmos, we do get 4,080. Now my second step is to do my probability. So what's the probability, though, of selecting the, I'm going to underline that because I'm going to come back to it, the 3 members. Now why am I underlining the? Because there is one way in which the 3 members that currently hold the position are also chosen. That's what we have to understand. So the 3 members that currently hold the position, they could get voted again. They could serve again. Even though they're equally likely to serve any of the positions, they could serve again. So that means it's not only permutation because it's rank, but it's also, it tells us the probability of choosing the 3 members, and that's only one option out of all the other options. You can range them. So out of one option of the 4,080, and this reduces down to 0.0002. So this is a very, very slim chance that those who currently hold office will also be elected again. Okay? Those who currently hold office will also be elected again. Right? Now, I'm going to erase this so we can have more room to work. Let's think about it a little bit more deeply. Student Advisory Board consists of 20 members. 2 members serve as the board's chair and secretary. So each member is equally likely. What's the probability of selecting at random the 2 members who currently hold? So it's very similar, actually. So we have 20 permutation 2, 20, and then we're choosing 2 out of that 20. This gives us 380 if we plug into the calculator. And then the second part is doing the probability. So of selecting the 2. So the 2 who currently are holding the position of chair and secretary. So what's the probability there? So 1 out of the 380 different ways, which reduces down to 0.003. Perfect. So that right there alone should kind of give us an idea of how these combinations, how these permutations, the fundamental counting principle are kind of related to probability. And you're going to be practicing a lot more with your homework, but suffice to say that should help you kind of guide what we're doing here. I'm going to go through 2 more examples. There's actually 2 parts each in those examples so that we can kind of solidify it. A little harder examples. So finding the probability of being dealt 5 diamonds from a standard deck of 52 playing cards. This is a little bit harder, so we need to understand, first of all, that order does not matter. Why doesn't order matter? Because the deck is completely at random. Okay, so if it's not out of the packaging, it's ordered if it's out of packaging, but the deck is completely at random when you first start playing. Okay, if it's not out of packaging, which tells me it's combinations. So if it's combinations, the first part I'm going to think of is the possible ways. So the possible ways of choosing. So the possible ways of choosing 5 diamonds out of the 13 diamonds that I have. What is that? Okay, that is literally 13C5. So I can choose 5 diamonds out of the 13 I already have. But there's a total here, and that's my second part. What's the actual total? The total out of all of the cards, not just the diamonds here, but out of all the cards is 52C5. Why? Because that's the possible ways of choosing just 5 cards in general. Not out of just the diamonds, but out of the total deck. So now, putting it all together, what we can have is the probability of choosing 5 diamonds equals 13C5 all over 52C5. So after looking at it, you're like, oh, that's pretty intuitive. And yeah, it is. You're right. It is pretty intuitive. Okay, and what we do here is literally just like we do anything in Desmos. We go over here, and then we can change this. So let's just change this to 13. So 13 and then C5. And now the cool part is we can literally just divide by. And we can do the exact same thing. So N and then CR. And now we can finish up with the 52 and then comma 5. And we get this low number. Basically, I'm going to round that 4 to that 9 up to that 5 here. So that 9 rounds the 4 to a 5. So that means when I go back, what is that probability? It's going to be 0.0005. So that is still less than 1%. That's the probability of being dealt on a deck, of any deck, just straight out of the 52 card deck is less than 1% of getting all 5 diamonds. That's pretty hard, and that's why poker is so hard to play, okay? Now, of course, if you weren't the first to be dealt cards, then you can calculate the probability after so many cards being dealt. What's the probability of being dealt multiple diamonds after maybe 2 people have been dealt their 5 cards? Then it would be dependent probability, right? And then you'd be multiplying certain things together. And we will be doing that, okay? So let's move on. I'll be showing you some of that. So in this case, this is a similar example. How about that? A similar example. Find the probability of being dealt 5 diamonds from a standard deck of playing cards that also includes the 2 jokers. So now it's not out of 52 standard deck, but it's out of 54. So now the first one, okay, the first thing I want to be considered is, all right, if the joker is considered a wild card that can represent any card in the deck, that means it can represent a diamond. So if it can be representing a diamond card, that means not 13 out of 50, or not 13 out of, not 5 out of 13, not 5 out of 13, but now we can do 5 out of 15. So 15C5 equals, and I can plug that in and I can get 3030, 3003, 3003. Okay, second, 54, because now that's my new total. I want to find the total. Okay, this right here was my total, not just the total out of diamonds. This is the total out of diamonds. I want to find my total because a joker is used as a wild. So this right here includes the jokers. Okay, now 54C, I still want my 5. And in order to do that, we can just plug it into the calculator and we get 3,162,510. And then my actual third step is the probability. So the 5 diamonds, and then including jokers, the 2 jokers that I'm including in the deck. What is that? Well, really now it's just I take these 2 numbers and put them on top of each other. That's all it is. It's 15C5 all over 54C5. Or it is 3003 all over 3,162,510. I'm not going to go ahead and show you that, but you can definitely come back here and change those numbers. Okay. In fact, you know what? I will, just because it's easy. It's right there. So I'm going to change that to 15, and I'm going to change this to 54. And then I get this really low number. It's about 0.0009%, or 0.09%, but 0.0009 probability. So 0.0009 probability, and boom, that's my answer. So you see how these probabilities can be used. I'm going to go through 2 more examples, one that actually involves a fundamental counting principle, and these are very difficult to kind of piece together, and they have to do a lot with complements as well. So try to pay attention as much as possible. We'll go through them. So a food manufacturer is analyzing a sample of 400 corn kernels for the presence of a toxin. In this example, 3 kernels out of the 400 have dangerously high levels of the toxin. Now, if 4 kernels, just random kernels, are randomly selected from the sample, what is the probability that exactly 1 kernel contains a dangerously high level of toxin? So how do we even go about this? I'm going to try to do it in steps again. Okay. Well, first of all, we have 3 total kernels, and 1 out of those 3, this is like choosing 1 toxic out of 3. So choosing 1 toxic, if I can spell toxic. Wow, still can't spell toxic. Toxic out of 3. Because again, it says in the problem, okay, so presence in the sample, 3 kernels have a dangerously high level of toxin. So I need to know what's the probability, what's how many different ways can I choose 1 toxic kernel out of the 3 toxic kernels, okay? My second step is to analyze it a bit more further. So out of 397 kernels, I can choose 3. So this is the choosing, not the toxic, but this is the choosing the non-toxic. Toxic, okay, out of 3, okay? 397, sorry, out of 397. choosing choosing three non-toxic out of 397. So far what we got is 400 total kernels. Now, 3 of those kernels out of the 400 are toxic. So we have 397, but plus 3 gives me 400. Okay, there's 3 total kernels that are toxic, but I want to know, what's technically the probability of choosing one of those toxic kernels. So now I start putting them all together. Okay, I start putting them all together, and this is going to be slightly my third step because I want to find the total. What's the total? Okay, think about it. Well, if we did 397 plus 3, and that gives me 400, and then this is the 4 toxic kernels. I'm choosing 4 toxic kernels, but 3 of them are toxic. Okay, so again, I'm choosing not toxic kernels. I'm choosing 4 kernels in general. Choosing 4 kernels in general, but 3 of those kernels that I choose out of the 4 could technically be toxic. Okay, so how I put this together is I'm going to find the probability of choosing one toxic kernel. I have technically 3C1, so choosing one toxic kernel out of 3 times 397C3, choosing 3 non-toxic kernels out of the 397, all over the total of 400 kernels together, total, while I'm choosing 4 of those kernels. Okay, so I'm choosing 4 kernels out of 400. I want to know what's the probability of choosing one kernel that contains a dangerously high level of toxin. Okay, choosing one kernel right here that contains a dangerously high level of toxin. But I also need to multiply that because of the fundamental counting principle. Okay, this right here is the fundamental counting principle, the different options that occur. I need to multiply that by the non-toxic kernels. So this is a very tricky problem. You won't really see a lot of these problems at all, to be honest, so don't freak out. But if you're in honors, you more than likely will see some of these problems, okay? But after I put all that together, and yes, you can just plug it in exactly how you see this on Desmos, besides the fact that you're going to be using these fancy tools, okay? But you can still plug it in Desmos, and what you get is a rather pretty low number. It's 0.030. It's like 0.029, but it rounds to 30. Okay, so roughly about 3%. So you do have a 3% chance of getting, one of those toxic kernels out of the 4 that you choose from the 400. Okay, so that one was rather kind of lengthy. The next example, I'm going to kind of skim it down and just kind of intuitively think about it. So let's erase this. A jury consists of 5 men and 7 women. So how many total? We have 20. So that's the first thing I want to do. Or sorry, not 20, 12. So we have 12 total. Okay. 3 jury members are selected. So out of the 12 total, I'm selecting 3. So now, just intuitively, I'm thinking, okay, 12C3. And now that's not that bad, right? And we could have done that here. We had 4 kernels out of a total of 400, right? So we could have jumped that gun there. So far, the total is secure. Now we want to know, okay, the probability of selecting that all 3 are men. So all 3 are men. So there's no women out of the 7 I choose. But out of the 5, I'm actually choosing 3. Now think about what I just said. No, 0 women out of the 7 I'm choosing. But I want to see what the probability is of choosing 3 out of the 5 men. 3 out of the 5 men, 0 out of the 7 men, or 7 women. What does that sound like? Well, so this is 7C0. I'm choosing 0 out of the 7 women, but because I want to see how many different events can occur. That means I need to multiply them together because that's a fundamental counting principle. Okay. Because I want to know how many different events can occur. I need to multiply them, but I need to multiply them with the different options of men, the different combinations of men. I don't care the combinations, so I'm going to just use combinations again. 5, but I want 3 total men, so C3. So now notice that 7 plus 5 gives me 12, and 0 plus 3 gives me 3. So it is a total, okay? So it definitely does work out theoretically. When I simplify this, I get 0.045, or roughly 4 or 5%, okay? Awesome. That is literally the additional topics in probability in counting. Additional topics in probability and counting. I hope that wasn't too bad. All right. What we learned was found the number of ways to group objects that can be arranged in order. That's permutation. We found the number of ways to choose several objects from a group without regard to order. We also learned how to use the counting principles, the fundamental counting principles, to find probabilities. Okay. Awesome. Now, you will have a homework quiz tomorrow, but that's the only homework quiz that you'll have this week. 3.4, go through Math Excel, additional topics in probability. If you guys have any other homework, please let me know. I will be collecting these notes this week, so make sure you're writing down your notes. But until next time, guys, email me with questions. This is C Squared Mathematics. Be sure to like and subscribe.